Okay, for the fuel system itself, there's not so much that I can show you. Normally you'll have a fuel pump, you'll have some injectors, or some means of delivering the fuel to the combustion space. But what you'll always see are fuel filters. That may be one of these here. I'm guessing it's the one on the left. Or actually it could be this one on the right, because the fuel filter is normally smaller than the lubrication oil filter. But anyway, you'll see a filter. Sometimes it's quite small. It'll be on the underside of your car between the fuel tank and the engine itself. And if we go on the top of this engine, we may be able to see the fuel injectors. You can see there is a fuel injector here. And the fuel injector connects into our combustion space, which we saw a little bit earlier. Fuel may be diesel or petrol/gasoline. But there are also gas-fired engines as well, and theoretically I suppose there's no reason why you couldn't use pulverized coal dust. I believe that's originally what internal combustion engines were fired on. For the fuel system itself, there's not so much I can show you using 3D models, but what I can tell you is that normally you'll have a fuel tank, a fuel pump and a filter. Perhaps you'll sometimes have two filters, a primary and a secondary filter. And you'll have a means of delivering the fuel to the combustion space, and that will be via an injector or by some other means such as mixing the fuel in with the air. Sometimes injection of fuel into the combustion space will be done mechanically. You'll use a very similar setup to that which we saw earlier when you were opening and closing exhaust gas valves or air inlet valves. But you'll have something different that comes off the camshaft, and that will be for opening and closing the fuel injectors. Many modern engines use a completely electronic control system to time when injection occurs in the engine. That's simply to increase the engine efficiency a little bit, although the downside here is that any problems you have with the electronic side of the engine will render the engine more or less inoperable. Because if you can't time the injection and control when the valves open and close, etc., the engine simply won't work. That's one of the big weaknesses of modern engines. They're so heavily reliant upon electrical systems. Personally, if I had the choice, I prefer a totally mechanical engine. They just run and run. They never stop. They're very, very reliable, but the downside is they are slightly less efficient than very modern high-tech engines. Let's load a 3D model up now so we can look at the air system. Okay, so to look at the air system, what I actually want to do is give you a bit of a case study and an example. Really speaking, if you want to talk about the air system, I suppose we could just say the air has to get to the combustion chamber because we need the oxygen from the air, and then after that it gets burnt and it turns into exhaust gas. So that's pretty much it. You need to get the air to the combustion chamber, and that's its job then finished. Let's have a look at a working example though, and for this particular 3D model we're going to have a look at an engine with a turbocharger, and turbochargers are quite common on diesel engines. So let me run you through the system quickly, and then we'll run through it in a bit more detail afterwards. So here is our turbocharger. It's got this snail-like shape. Come around here. See it from this angle. You see, very unique shape. There's quite a lot happening here. Blue signifies air. We're sucking air into the turbocharger because the turbocharger is actually rotating, and I'll explain to you how that works in a moment. We suck the air in through what we call a compressor or compressor wheel, and we compress the air, and then we force it around this snail shape called a volute. So the snail shape is called a volute casing. And what we're actually doing there is we're changing the velocity of the air and converting it to pressure energy. So from kinetic energy to pressure energy. So we've increased the pressure of the air. And I'll explain to you why we do that in a moment as well. The air comes along down here. It's going to come along here. And then we go into an air cooler. We cool the air down slightly. We send it then to the combustion chamber. See from the top, comes off. Goes to air inlet valves. They open and the air is forced in because the pressure of the air within the air inlet manifold is higher than in the combustion space, and that's what allows the air to flood in, and we get a little bit of valve overlap, so some of it flows out the exhaust gas port, flush the bit of exhaust gas out, and then our air system is finished. To completely understand the model though, let's follow the exhaust gas system. So we have the two exhaust gas valves coming out here, exhaust gas comes along, and then, rather bizarrely, they come down here, and the exhaust gas connects onto the turbocharger. So here's the exhaust gas manifold, and it joins onto the turbocharger, goes around, and then exits out of the turbocharger turbine. So that's quite interesting. Why would we do that? Well, let's have a look at the system in greater detail. When the exhaust gas comes out, it's going to pass over this turbine, and it's going to cause the turbine to rotate. When the turbine rotates, it's actually on a common shaft. So let's come along here. You can see it's on the same line as the compressor wheel. It will be coming along. The shaft runs through the middle. So when the turbine rotates, the compressor wheel rotates. That means the more the turbine rotates, the more the compressor wheel rotates. Imagine you had two wheels connected on a common shaft. Now if you spin one wheel, the other wheel is going to spin as well. And that's exactly what's happening here. So we're drawing more air in because the turbine is going faster. We compress the air, and when we compress it, the temperature increases. Remember we said earlier, if you compress a gas, the temperature increases as does the pressure. Because we increased the temperature, we take the air and we cool it down. We cool it down because the more we cool it down, the more air we can get into the combustion space, which means we have more oxygen available for combustion. That's the purpose in this whole turbocharger setup. We want to compress the air so we can get more of it into the combustion space. And we want to cool the air once again so we can get more of it into the combustion space. The air comes out and then it goes to the combustion space. And after that, we get the exhaust gas out. Let's see if I can line this up better. The exhaust gas comes out and goes back to the turbocharger. Now, if you've ever heard of a concept called turbo lag, the reason we have turbo lag is because it takes a while to get more air to the engine, and then it takes a while to get more hot exhaust gas to the turbine. Turbocharged engines take a while, typically a second or two, to really get into motion and to get the turbine rotating very quickly. And until that turbine is rotating very quickly, we can't suck more air into the compressor wheel, which means we don't have the oxygen available in order to release more power. So that's turbo lag. The other thing that you're going to see on all engines normally is an air filter. Filters are a big part of engineering. You install them because you want to remove particles from a system or prevent them entering a system in the first place. Now, we don't want to suck just normal ambient air into our engine. There might be bits of dust floating around. There might be bits of sawdust. Who knows? Imagine you drove past a wood chippings factory or some other sort of factory. All of that dust in the air will get sucked into your engine unless you have a filter. If you have a filter, you'd install it shortly before the turbocharger. And this means that as you draw air into the system, it's going to be filtered and we end up with clean air going into the engine. If the engine doesn't have a turbocharger, then you'll install the air filter simply on the main air inlet. And you have to change this filter periodically, the same as with a lube oil filter, which is a lubrication oil filter, and a fuel filter. So filters are very important if you want to own and operate your engine for a very long period of time. Now, I was going to do a separate video for the exhaust gas system, but I don't think that's really required. The exhaust gas system will usually be, at least on medium-sized engines, simply an exhaust gas system like that shown, especially for medium-sized diesels, and it will go to the turbocharger, and then maybe it passes through some sort of noise reduction apparatus or component, sometimes called a silencer or a muffler. And this means that we're not creating a lot of noise with our exhaust gas system when it comes out of the exhaust gas pipe. On engines that don't have a turbocharger, then you can discharge the exhaust gas directly to atmosphere. Important to realise though that the larger the engine is, the more complicated the exhaust gas system will become. If you have an exhaust gas system with a very large diesel engine, the exhaust gas may have to be cleaned before it is discharged to atmosphere. That's just modern common practice. You can't just dump exhaust gas into the atmosphere like we used to do 100 years ago. So in order to comply with environmental pollution legislation and laws, you'll sometimes have to clean the exhaust gas, which means taking the burnt carbon out of the air, for example, before you discharge it to atmosphere. But anyway, I hope you now understand how the air system works and some of the components you're likely to encounter, and I hope you also understand exactly how the exhaust gas system works. They're relatively simple systems, but as with many things in engineering, the bigger the system becomes, the more complicated it becomes, and the more complicated all the components become. So we covered 4 systems. Let's go and have a look now at the cooling water system.